Now we will see the very important concepts of the state space model are controllability and observability. Let us see what is the controllability, the concept of controllability. A system is said to be completely controllable if all the states of the system can be transformed from any state to final state within a specified time with available input. Otherwise, the system is said to be uncontrollable. What does that mean? Let us say there are 5 states in the system. So those 5 states can be transferred from initial state to any other specified state within a given time and with available input. Then we say that particular system is completely controllable. So if all the states are able to transform, then it is called completely controllable. Even if the one state is unable to transform, the state is not changing within a time with available input, then it is uncontrollable, we say. So which means the other way, is there any input available such that all my states will be transferred from initial state to final state? If it is available, then system is said to be controllable. So this controllability is very important when you design state feedback controllers. Then how to test it? So we have a Kalman test to find the controllability status of the state model. So what are the test conditions? If the rank of the controllability matrix, we will see later what is the controllability matrix. If the rank of the controllability matrix is equal to the order of the matrix A is a system matrix, then system is said to be completely controllable. So if the rank of controllability matrix is less than the order of the matrix, then it is uncontrollable, and the rank gives how many uncontrollable states we have. So the rank of controllable matrix we need to find, and we know already what is the order of the A matrix. Then we need to compare these two. When these two are same, then we say all my states are controllable. So if it is not equal, whatever the rank we have, that gives those many number of states which are uncontrollable. So what is the controllability matrix? With the help of A and B matrix, then we can write the controllability matrix M. So M is, we can write B, AB, A square B, and so on up to A n minus 1 B. So this is called controllability. That means you take the B matrix, substitute here, then again you multiply AB and concatenate here, again you concatenate A square B, and so on. So you will be getting the matrix M, which is called controllability matrix. Then I need to find the rank of this matrix. If the rank of this matrix is order of A matrix, then the system is completely controllable. When I say controllable, it means it is completely controllable only. Uncontrollable means there are one or more states which are not controllable, which cannot be transferred from initial state to final state for a given time and also the available input. So we can also find the controllable state as by looking at the M matrix. If determinant of M is not equal to 0, then we say system is completely controllable. So if determinant of M is equal to 0, it is uncontrollable. So we already know what is M matrix. You just find on the det of what. So det is not equal to 0, completely controllable. If det is 0, it's a singular, then we call this uncontrollable. So as I said, this controllability is very useful to design feedback controllers. Similarly, we have another concept called observability. So the definition of observability goes like this. A system is said to be completely observable if all the states of system are observable, means measurable within a specified time. So with the help of the outputs, by observing the output variables, then we say system is observable. Otherwise system is unobservable. So in this case, I want to measure outputs, and from the outputs can we derive the states of the system, whether all my states are observable or not. Can we find the states from the available outputs, which is called observability. So if one or more states are not able to observe or not able to measure, and then we call system is unobservable. So we can have the Kalman test again to know whether the system is observable or not. So if the rank of the observability matrix is equal to again the order of A matrix, then system is said to be completely observable. and if rank is not equal to the order A, then we say system is unobservable, and the rank gives the number of unobservable states of the system. Then what is observability matrix? So we can by using A and C matrix, we can define the observability matrix N. So N is equal to, it is going to be column, and C, CA, CA square, and so C n minus 1. So you take C matrix, you place here, again the next row it is CA, and next row it is CA square. This way you can find out N. And the test is very clear, the rank of N matrix is equal to order of A, it is completely observable. So if it is not equal, it is unobservable. The other way also you can do, take N matrix, find the delta of N. If delta of N is equal to 0, it is unobservable. If delta of N not equal to 0, then the system is observable. Again, the concept of observability can be used to design state feedback controllers of the system. Then we can look at some of the important points of controllability, observability. So all the real-time systems are completely observable and completely controllable, all my real-time systems. And if the state model is represented in standard forms like controllable canonical form, observable canonical form, or a diagonal canonical form, then we say that particular system is completely controllable and as well as completely observable. So if there are any pole zero cancellation, let us say I am trying to get the transfer function model from state space model. So if there are any pole zero cancellation, then we can say that now the system may be unobservable or uncontrollable. So if there are no pole zero cancellation, then we say system is completely observable and completely controllable. So this way we can say the controllability and observability matrix. We also have the concept of stability. So we know stability in transfer function model, if you have closed loop poles, all the poles are lying left of the S-plane, we say system is stable. If there are one or more non-repeated poles on imaginary axis, system is marginally stable. If the poles lying in right of the S-plane one or more, then we say system is unstable. Then state model also we can obtain the same thing. For that what we need is, we need to write the characteristic equation with the help of the matrix A. So how can you write the characteristic equation? We know Si minus A det is equal to 0. So with that we can find out the characteristic equation and find out the roots of it, or else lambda I minus A det is equal to 0. This lambda roots are called eigenvalues of the system. By looking at the eigenvalues, we can see whether the system is stable or not. So if the real part of all the eigenvalues is negative, then we say system is stable. If one or more real part is positive, then system is unstable. So if you have purely imaginary part which are non-repeated, again we say system is marginally stable. So this way you can find out the stability of the system. We also have the another concept called output controllability. So what is this output controllability? So output controllability describes the ability of the external input to transform the output from any initial condition to the final condition within a specified time. Now here not about the state, it is about the output. So output can be transferred from one state to other state with external input, if that is possible or not. So if so, we call the system is output controllable, otherwise output uncontrollable. Then we have a small test here to know whether the system is output controllable or not. Let us define output controllability matrix. So this MO stands for output controllable, is we can CB, we have CAB, CA square B, and so on, Cn minus 1 B. So with the help of A matrix, B matrix, C matrix, we can define output controllability. And once you have again the same thing, if the rank of this matrix is equal to order of A, then we say system is completely output controllable, otherwise it is output uncontrollable. Or we can find the data of this M naught matrix, if it is equal to 0, output uncontrollable. If it is equal to 0, not equal to 0, it is output controllable. So this way we can find out the output controllability of the system. So the controllability matrix is M. So this controllability matrix we call it as state controllability matrix, or the concept of controllability refers to always state controllable, but we have output controllable. Now if the system is state controllable, completely controllable, it need not that the system is always output controllable. Or if the system is completely output controllable, we need not we say that the system will be completely state controllable. These two are two different concepts. So one is not related with the other. It's all depends on A, B, C matrices of the system.